Hello, in this video, I want to talk about how to fit a polytomous logistic regression using R. So the polytomous logistic regression is also called multinomial logistic regression. This is when the dependent variable is a categorical variable more than two levels. So if you have 0, 1, then it's a logistic regression. But if you have, say, 0, 1, 2, three categories or even more, okay, then it becomes a polytomous uh, dependent variable. And of course, among these categories, there's no order, okay? If there's an order among these categories, then we need to run an ordinal regression model, which is a different topic. Okay. All right. So first, let's set random seed. Let's create a data set, sample size 500, with three independent variables: x1, x2, x3. X1 is continuous, draw from a normal distribution, and then x2 is a binomial variable, and x3 is a categorical variable with three categories. Okay, and then we kind of calculate different linear combinations of these three variables, eta 1 and eta 2. And then let's exponentiate those and then calculate a denominator. And then we have the probabilities for the three categories, 0, 1, and 2. And then we generate the dependent variable and make sure it's a factor. And we combine these probabilities and then do the random sampling, and then we pull y, x1, x2, x3 together into a data set, and this is what it looks like. Okay, so y is a dependent variable with I think 1, 2, 3 or 0, 1. Let me double check on that. So here, so if I do data y, yeah, it's a 0, 1, 2. Okay. All right. So in order to fit a polytomous logistic regression, we need actually a neural network package called nnet. So let's load the nnet, and then there's a function called the multinom. Okay, and that's the function we use to fit a polytomous logistic regression. And the syntax is really the same as most of the regression models in R. So we specify a formula, y tilde x1 plus x2 plus x3, and data equal to data, okay? And then we can simply just say summary of this model, and then you can see the formula, and then you get the coefficients. You have three categories, then you have a model 1 and a model 2, okay? And you got the intercept, you got the beta coefficients for each and every independent variables, and also you got standard errors, and you get the residual deviance, and you got an AIC value. So when you see an AIC value, you know you have the log likelihood. So the parameter estimation for this function is maximum likelihood estimate. Okay, and as we know, if you have maximum likelihood estimation, then you have a lot of things you can do with the model. But let me just using the structure to take a look of what's are in this model object. So you can see it's a list of 26. Okay, so got a lot of informations in there, and you can glance through all this, but you do see the AIC value at the last. Okay, so we can extract, for example, the coefficient, which is already printed out by the summary statement. One thing we don't have is actually the p-value for testing the significance of the effects. Okay, and unfortunately, it's not by default of this multinom function. So we have to do a little bit of programming our own. So first we can calculate the z-values using the coefficients and the standard errors. And then we can calculate the p-values. We're doing two-sided test, and we can print out the p-values. And remember, these are the p-values for two models. Okay, so you can see for model 1, the x1, x2 are significant, but x3 is not significant. Okay, for model 2, nothing is significant. Okay, and of course, if you want to compute the odds ratios, we can just exponentiate the coefficient. And then if you want to calculate the confidence interval for the odds ratios, use exponentiate of conf int. Okay, and then you can print out the odds ratios, also print out the confidence intervals. Okay. All right. And remember, we have maximum likelihood estimate, so we can perform a likelihood ratio test for nested models. For example, if we want to test if x1 is significant, compared to the full model, then we can fit a model without x1, but with x2 and x3, and then we can compare that model with the full model using likelihood ratio test. Okay, so first let's fit the model x1, so it's a y tiered x2 plus x3, so without x1. And then we can use the ANOVA function. So ANOVA model x1 and model test equal to chi-square, and we can print out the p-value. So you can see the p-value is 0.03. So x1 is a significant factor by the likelihood ratio test. Okay. So the previous p-value we computed by doing some coding are p-value from the world test. Basically, it's a z-test or a t-test. Okay. But likelihood ratio test has several advantages. For example, it performs relatively better than the world test when the sample size is relatively small. Okay. All right. Once you have fitted model, you can also do predictions. So basically, you can use the model, but then you can use the original data, do predictions, and you can calculate the accuracy. Basically, the mean of prediction equal to the data of y, okay, the true data. So the model accuracy is about 73.6%, which is okay, all right? Okay, so, and we can also do likelihood ratio tests for goodness of fit. We can load in the library mass, and then we can fit a null model. The null model is a model with only the intercept. And then we can calculate the deviance differences between the null model and the model where they fit it, and then calculate the difference in degree of freedom, and then you can use this p chi-square because the deviance difference will follow a chi-square distribution. Okay, so then calculate the p-value and say the likelihood ratio test of p-value is So it is very small. So it's just saying the model we fit is significantly different from the model with only the intercept. Or in other words, it's worthwhile to fit this model. Okay. And also we can extract the residuals and we can print out the residual plots. But since the dependent variable is categorical, not sure how useful these residual plots are, but let's just do it. Plot it out. And okay, it looked like that. Okay. So yeah, the fitted value versus the residuals. The two lines look to be parallel, and then for the QQ plot of residuals, there's a little bit of deviation in the tails, and for the residuals histogram, you can see the residuals are all within -2 and +2, so the model fit is relatively okay. And then you can see the response category for the residuals, but you can see it really is better for the categorical one. Okay. So all right. So it has limited outputs from this function for the Polytomous Logistic Regression model fitting. Okay. But yeah, I think we covered the model, the estimation, and inferences, and did a little bit goodness of fit, as well as residual plots. Thanks for watching.